It turns out that this is a fairly well-known form of a differential equation, and somebody has done all the work to solve this equation for us. So all we have to do is apply our boundary conditions and make sure that we are choosing only the solutions for our radial dependence that are good wave functions. So these need to be good wave functions. And remember that means, so remember that our R variable can go from 0 to infinity. In other words, 0 is at the nucleus. So the electron can be near or at the nucleus, and it can go all the way out as far away as it wants from the nucleus. So that's our bounds for R. And so for our radial dependence to be good wave functions, R at 0 cannot go to infinity or minus infinity, and R at infinity cannot go to plus or minus infinity. So we can't have our wave function be infinite. It has to stay finite. It needs to be single valued as well, and we have to insist that it is continuous and differentiable. So when we apply these boundary conditions to the solutions to this differential equation, we find that only certain values of L will work, and furthermore, there are only certain values of N that are integers, which will give us appropriate good wave functions. And so we can write our R solutions, and they're going to depend on both the N and the L quantum numbers now. And remember, those quantum numbers come from the fact that we're picking out the good wave functions, and they come from our boundary conditions. And so that's going to be equal to this complicated function, 4 times z cubed n minus L minus 1 factorial divided by n to the 4th a naught cubed n plus L factorial raised to the 3rd power, this whole thing to the 1/2, and then I'm going to have 2zr over n a naught raised to the L, e to the minus z r over n a naught, and then I'm going to have these polynomials that depend on n plus L and 2L plus 1, and our functions of 2zr over n a naught. So that's a big, ugly looking equation, but if we think through this a little bit, we can digest this a little bit better. So this whole thing right here is just my normalization constant. So this is just the thing that ensures that my functions are normalized. Notice that we have this exponential part that is multiplied by these polynomials. So these are particular polynomials, and they're called the associated Laguerre polynomials. And this should be familiar to you because other solutions that we've seen are exponentials multiplied by a polynomial. We also have this a naught term or constant that has showed up in our solution. So let's define what a naught is. So a naught is equal to 4 pi epsilon naught times h bar squared over the mass of the electron times the electron charge squared. So notice that we've just combined a whole bunch of constants that show up in our Hamiltonian, and this has units of distance. If we plug all these constants in, we get a value of a naught equals 0.529 angstroms. Remember that an angstrom is 10 to the minus 10 meters. And this is exactly equal to the value of the first n equals 1 Bohr radius in the Bohr atom. And so A naught is called the Bohr radius. Now we can also see that this 2zr over NA naught shows up as a variable pretty much in each part of this equation. So let's think about what 2zr over NA naught might be. So we're going to call that rho, and it is going to be the variable that we use in this equation. And notice that 2 has no units, z is just the atomic number, it has no units, n is a quantum number, it has no units, r has units of distance, and A naught has units of distance. And so this is a dimensionless variable. And just like in some of our other solutions, we're going to write these solutions in terms of this dimensionless variable, this variable that doesn't have any units. And so that means that I can write my solutions in terms of rho. And so I have some normalization constant that depends on L and N times rho raised to the L times e to the minus rho over 2 times my Laguerre polynomial, which depends on n and L, as a function of rho. So this is the solution to the radial part of my hydrogen atom problem. This table shows some of the associated Laguerre polynomials that solve our radial problem. The other thing that we need to talk about is the restrictions on n, L, and m. So we already know from the rigid rotor problem that L can be 0, 1, 2, etc., and that my m's are going to be equal to minus L all the way up to 0, all the way up to plus L. And furthermore, when we solve the radial part of the problem, we find that n can only have values of 1, 2, 3, so forth and so on, and that a restriction on L appears when we solve the problem and match the boundary conditions to make sure that we have good wave functions. So it turns out that L can only go up to n minus 1. And so you'll notice that these are your familiar restrictions on the quantum numbers for the hydrogen atom that you learned in general chemistry. These come from the fact that we have to make sure that all of our wave functions are proper, good wave functions, single-valued, continuous, finite, and differentiable. And so when we apply those boundary conditions, that's where these restrictions on the quantum numbers come from. No solution to an eigenvalue problem is complete until we know what the eigenvalues are. And when we solve the radial equation, we find that the eigenvalues depend only on the quantum number n, and they're equal to minus the mass times the atomic number squared times the charge on the electron to the fourth divided by 2 h bar squared times 1 over 4 pi epsilon naught divided by 1 over n squared. And so all of these things are constants, and we can write this in terms of our definition of the Bohr radius, A naught. So if we do that, we have En equals minus E squared, Z squared, atomic number squared, divided by 2 times the Bohr radius times 4 pi epsilon naught over n squared. The following combination of constants has the units of energy. So if we take the charge on the electron squared divided by 4 pi epsilon naught times the Bohr radius, that has units of energy And we call this energy a Hartree. So E sub H is called a Hartree. That unit of energy is used frequently in thinking about atomic energies. So if we write our eigenvalue then in terms of the Bohr radius and Hartrees, we get that it's equal to minus the Hartree, unit of energy, atomic number squared, divided by 2 times 1 over n squared. And if you want to think about this in terms of your familiar equation from freshman chemistry or from first year chemistry, the energy of any n level was always written in terms of z squared times the Rydberg constant times 1 over n squared. And so the Rydberg constant is just a half of a Hartree.